Okay, so 7C is the law of large numbers. It's our last section in chapter 7 for probability. Now, we'll introduce the law of large numbers by thinking about tossing a coin. Right? So a single toss of a fair coin will get heads or tails. We've seen that the probability of landing heads is 1/2. What that means is one out of every 2 times we toss the coin, we'd expect to see one head show up. Well, pretend we toss the coin perhaps maybe 10 times, and we'll get a random listing of heads and tails. Let's make sure we get 10 written down here. And perhaps we arrive at a string like this. Our first toss was heads, second toss was tails, all the way through to the 10th toss. Now what happens is, in this situation, the frequency of heads that we saw in our actual experiment where we actually tossed a coin, it'll allow us to calculate the relative frequency of heads. Well, there are 1, 2, 3, 4 heads out of 10 total tosses. So that's 4 out of 10, which is 0.4. Okay, and that's a little bit different than what we normally calculate for our theoretical probability of 1/2, which is 0.5 as a decimal. So there's a little bit of a disconnect here. 0.5 is our theoretical probability, and 0.4 is our relative frequency for this number of heads in this single round of the experiment, tossing the coin 10 times. So the reason that we don't have a matching theoretical probability versus our observed relative frequency in any random experiment we might do is exactly because of that. There's randomness in this situation. So this randomness creates a little bit of noise, and it makes this value not exactly equal to this value. Now, what the law of large numbers actually tells us is that maybe we do 100 tosses. Okay, and then suppose 51 of those were heads. Okay, well then our relative frequency in this situation comes out to 51 over 100, and that's equal to 0.51. And what we see is that this number here is getting quite a bit closer to the number 0.5. Now, we didn't actually do this, but we could do this. We could verify it experimentally, flipping a coin a bunch of times, or even simulating it with a computer. What the law of large numbers says to us is that the more times we toss this coin, the closer our relative frequency probabilities are going to get to our theoretical probability. So for a general event, if we're interested in an event A and it has theoretical probability A, so the more we repeat these trials to observe this event, the proportion of trials in which the event A occurs will be close to the value of the probability of A. So repeated many times, right? The more we repeat this, the closer the relative frequency gets to the theoretical probability. So that's essentially the law of large numbers, okay? Now, let's see it at work. We're going to use it to translate expected value calculations. And expected value calculations will be our last main calculation for probability in this chapter. Now, let's look directly at the formula to start. The expected value to the player or to the house or to one player or to another player, and expected by a certain set of events. We can think of these as winning events or losing events. It's the value of event 1 times the probability of event 1 plus the value of a second event times the probability of that event plus the value of an nth event times the probability of an nth event. So in other words, there could be 2 events, 3 events, 4 events, 5 events, so on and so forth, right? As many as we like finitely. And we can calculate this number called the expected value based on that. So expected value has perspective to it. It's either from one player or another. So when we talk about the value here, it depends on whether or not this is a loss of value or a gain of value, so negative or positive with respect to order. Now, either from one player's perspective, that's a loss, and the other player's perspective, it might be a gain. So let's see this take place in the example below. So we're asked to find the expected value to the player. So good, we're told whose perspective to take in this calculation. We want the player's perspective of a $5 roulette wager on red. And this is where the bet will cost $5. In other words, the player puts $5 down on red. The house will pay out $5 if the ball lands on a red slot. So in other words, the player keeps their $5, keeps their chip, and the dealer slides another chip to the player. So the player goes up positive $5. So they gain plus $5 on their account, essentially. Okay, if red doesn't come up, the $5 that the player put down goes to the house keeps it, and the player goes down $5 or negative $5 to the player's account. So we really want to understand how money is being exchanged or how value is being exchanged in a problem like this. So the player either goes up 5 or down 5. Now let's see. A roulette wheel, let's remember, has 18 red slots, 18 black slots, and 2 green slots. So that's 38 total slots. So the expected value to the player, two-player expected value is equal to the probability. Well, there are two events, right? One event is that we land on red, or the ball lands on red, so it's probability that red comes up times the value that red comes up. We're just using the formula as we have it in the tan box above. Then the probability of, well, the way we lose money is it's not red. Okay, that's either green or black, but not red will suffice for either of those. Not red. Now let's see. The probability that it's red, there's 18 red slots out of the 38 slots total, times, well, what's the value if red comes up? Well, if the player bets on red and red lands, they're going to go up $5. So there's the $5 the player gains, plus the probability that red doesn't land. Well, there's 18 black slots, 2 green slots, so 20 slots that are not red. So it's 20 ways to lose out of 38. Times, if red does not come up, the player is going to lose that $5 they put down. So there's our calculation so far. What we'll have is 90 in the numerator on the left, put a dollar sign out front. So of 90 over 38, multiplying 5 times 18, and then minus 100 over 38. And this is negative 10 over 38. And as a decimal, it's approximately negative $0.26. In other words, negative 26 cents. So the expected value to the player for a bet on red in roulette is negative 26 cents. Okay? Now, what we see immediately is that the player's expected value is a negative number. We should keep that in mind. That's probably a bad thing, right? The player is going to, it kind of suggests to us that the player will lose money somehow. But the player never loses exactly 26 cents. After all, each of these bets is $5. You either gain 5 or you lose 5. So to make more sense of this negative 26 cents that we have for the expected value, let's look down the next part of the example. This might help to clarify. It says interpret the meaning of this calculation. So right here. Specifically, what would the expected value be if we made this wager 100 times? Okay, so the EV, expected value of 100 red wagers. Well, if that's the case, we just scale up our expected value by 100. In other words, we multiply 100 times the expected value of a single play, and that's negative 26 cents, single play, a wager, let's put wager, single wager. Good. And well, that's 100 times negative 26 cents. And that comes out to negative $26. It almost looks like it makes a little bit more sense, right? That's the answer to the second part of the question. What would our expected value be if we play this game 100 times? Well, we'd expect to be somewhere near negative $26 after 100 rounds. So in other words, we've won some money, we've lost some money, but after 100 times, we should be fairly close to negative $26. Let's say we play this game 1,000 times. Again, that $26 is problematic. We'll move on. It's problematic because how are you down exactly $26 on $5 bets? It's not possible, but we can be close. Negative $25 seems like it might be pretty close. Now, if we play 1,000 times, 1,000 red wagers, well, it's 1,000 times negative 26 cents, and we end up with negative $260. Now, this is the first time this has been feasible. Okay, now it starts to make sense. If we play 1,000 times, again, we won't land exactly on negative $260, but we should be pretty close. In fact, if we repeated the game if we made 1,000 red wagers every day, and then we took our average net earnings, we would find that we would lose about negative $260 each day, making 1,000 bets on red over and over and over again. We should get very close to that negative $260. So one way to interpret that negative 26 cents, just to come back to it, is this. We never lose exactly that much. We never gain exactly that much either. But playing this game over and over for a lifetime, making this bet, when we look back at each of the individual bets that we made on this and we calculate all our total winnings or losses, or our net earnings is the best way to express that, we'll find that on average, we lose 26 cents each time we make this wager. Now, an interesting thing about expected value is it's sort of complementary, or it's opposite. So if the expected value to the player is this negative 26 cents right here, well, that means that negative 26 cents on average leaves the player's purse, well, and goes to the casino. So the expected value to the casino, in this case, or whoever's hosting the game, EV to the casino, is exactly the opposite in sign. It's just positive 26 cents. There's sort of a net conservation of money here. So the casino gains about a quarter for every roulette wager on red, on average. That's essentially the house edge that people like to talk about. Okay, so a fair game occurs if the expected value is equal to 0. So if we calculate the expected value and it's equal to $0 or 0, whatever the value might be. Almost always we'll use dollars in this class. So a game in which the expected value is $0, well, that's the only time a game can be called fair. Now, if the expected value is positive in favor of the player, well, the player can now make a whole lot of money on that game because on average, they'll make that positive little bits of amounts. But that's essentially what the casinos do. They're very well researched, and it's pretty much a matter of time for the law of large numbers to catch up to you. So, okay, let's look at one more example similar to this. This involves a raffle. So we've gone to a raffle and purchased a $2 ticket. The raffle has sold 100 tickets, and it's going to pay out $50 to the winner of the raffle. They're going to select one ticket, and that person wins $50. So what is your expected value in this raffle if you have bought one of these tickets? So your expected value is equal to the probability that your ticket is drawn times the value of having your ticket drawn, right? Plus the probability that you're not drawn times the value that you're not drawn. Okay, so pretty easy to start. So we have the probability that our ticket is drawn. Well, we have one ticket. There are 100 tickets, so 1 out of 100 chance to be drawn. The value if we're drawn, well, we're going to win $50. We would almost close that up, right? We almost close parentheses and move on. But we're going to win $50, but we paid $2 to get the ticket. We're not going to get that $2 back. We're going to win $50. So we need to account for that. So even if we win $50, we're only going to go up by $48. That $2 is just gone and given away for good. Okay, so the most we're really going to win if we win that $50 is $48, as denoted in the parentheses. Okay, because that $2 goes to the fundraiser. Now, plus the probability that we're not drawn, 99 out of 100. 99 of those tickets are not ours. Times, well, if we're not drawn, we're just out our $2. Okay, and we've got $48 times 1 over 100. So we have 48 over 100 minus 2 times 99 is 198 over 100. And this is dollars as well. And 48 minus 198 is negative 150 over 100. And that comes out to negative $1.50. Okay, so that's a pretty extreme edge, but we can kind of see the situation. We have way fewer chances to win in this game because there are 100 tickets or 99 tickets that aren't ours out of the 100, and the payoff's not really that great. We're not going to be paid, enough to really raise up our expected value. There is a point where this value could be so large that this value could be positive, and if that's the case, it might make sense to play the game. There are some points where a lottery or a Powerball that states might hold, where the jackpot value might go up so high that the expected value is actually positive to the players. And some might argue that that's when it's mathematically plausible or mathematically sound to play a lottery, when your expected value is positive. Okay, so by definition, is this a fair game? That's our next question. This is not a fair game. The reason it's not a fair game has nothing to do with how we feel about it. It's not a fair game because the expected value is not 0. So we could say that like this: since the expected value is equal to negative $1.50, which is not $0. Okay, that's it. The definition of a fair game is one with expected value 0. Okay, so would the expected value of your ticket increase, decrease, or stay the same if the raffle was to draw second and third place winning tickets with prizes of $10 and $5 respectively? Well, I'll leave that one up to the reader, but think about it this way. Nothing changes for first place, but they're going to pay out $10 to a second ticket that's drawn and $5 to a third ticket that's drawn. Seems like you're getting more of an advantage, like you're going to possibly win at least some money. So it probably will increase. I'll let you reason through that. You could calculate it if you really wanted to. Now, let's see. I don't advise that calculation. It's not necessary. So one more thing to look at. And part of this will be exercise for the students. We're going to go to the game of Big Six, which was once popular in casinos in Vegas. Maybe not so much now. I don't know. I haven't been. So anyway, Big Six has 52 slots on it, on a wheel. Okay, and they're all given different denominations: the 1-star slot, 2-star slots, 5-star slots, so on up to a joker slot and a logo slot. So they're all listed right here. Okay, so a 1-star slot pays 1 to 1. In other words, if you put $1 down, you're going to get $1 back on that 1-star slot. If you put $10 down, you'll get paid $10 on that 1-star slot if the wheel lands on a 1-star slot. Okay, there are 24 of those, and it only pays 1 to 1. Okay, so if you look at the next category, the next denomination, 2-star slots, they pay 2 to 1. Okay, so if the wheel lands on a 2-star slot and you put $1 down, well, you get to keep your $1 and the house gives you $2, so you go up $2. Okay? Now the difference is there are only 12 of these. There are many fewer 2-star slots than there are 1-star slots. And you see, as we move down the list, we have fewer slots, 8, 4, 2, but better payouts. $5 to your $1 bet, $10 to your $1 bet, $20 to your $1 bet. Okay, so let's calculate some expected values here. I'll start with, I'm just going to do a few of these, not all. I'm going to leave the rest for students to do and to answer the questions that follow down below. So for the 1-star slot, let's find the expected value. The expected value to the player for a 1-star slot. So this is all with respect to the player. Okay, so the probability of a 1-star slot times the value of a 1-star slot plus the probability of not a 1-star slot times the value of not a 1-star slot. Okay, 1 star. All right, now let's see. The probability of a 1-star slot is 24 slots out of 52. And we'll be paid $1 for that. We'll keep the dollar we put down, and the house would pay us $1 because we landed on a 1-star. All right, plus 28 out of 52 other slots. That's the probability to land on something that's not a 1-star slot. And in this case, it's a negative $1 to the player. We lose the dollar that we put down. So this is 24 minus $28 over 52. Okay, and that leaves us with negative 4 over 52, which, to make it a little more simple, is negative 1 over $13. Okay, I know that's not so handy, but we could calculate that as a decimal and take it a little bit further. I'll leave that up to students to do. We see that it's negative, as we'd expect, and it's going to be some amount of cents. So not a big loss, but again, it's not very exciting. You put down $1, you might get your dollar back, or you might lose it. Okay, let's see. The expected value of, let's go to the 5-star slot. Let's go to the 10-star slot. Let's do that, 10-star. Okay, probability of the 10-star slot. Well, let me skip this part for the sake of room here. Probability of the 10-star slot, there are 4 of those out of 52 total. The value of the 10-star slot, if we put a $1 bet down, we're going to win $10 on this. That's getting a little bit more exciting. Plus, now the probability that we don't land on a 10-star slot, well, that's 48 out of 52. Times what happens if we don't land on a 10-star slot, we just lose our dollar. Okay, so now we have 40 over 52. These are all in dollars. Minus 48 over 52. And we find that we end up with negative 8 over 52 dollars. And simplifying that to a fraction, we'll have negative 2 over $13. Okay, I'll let the reader again convert that to cents, but I can tell you this much. Negative 2 over $13 is more negative money than negative 1 over $13. So in other words, we lose more, or our expected value is a bigger loss for 10-star slots than it is for 1-star slots. So it looks like so far, the better bet is the 1-star slot versus the 10-star slot. So now if the reader goes through and finishes up all the rest of these calculations of expected values, there's going to be one for every single one of these entries here. Okay, what you can do is from there answer the question of which one is the worst bet, which one is the best bet. Okay, and the last task, if you really want to try it good, this is sort of optional. This is extra, optional or extra, would be to see if you can adjust the payouts of Big Six to make the game exactly fair, to make each one of those expected values 0. So maybe you just do 1 or 2 slots just to get the hang of doing that, and you probably get the point. So there it is. I'll leave that exercise to you, and I hope you enjoy it.